little bit the lightning talk, so reduction can show that our problem is easy. They can, of course, show that our problem's hard. They can allow to show that proof techniques propagate between different problems, and the study of reduction raises new kinds of questions. It also helps to identify, and this is what we're going to do in this talk, identify central problems that their solution is going to imply the solution to many other problems as well. And it sort of will allow, or hopefully will allow, to generate some kind of taxonomy, again inspired by computational complexity, clustering the space of all communication problems into these clusters, finding maybe complete problems for each and every cluster, and in such as steering our research. And so last time I mentioned a bunch of different connections that have been sort of came up over the last few years between network coding, index coding, interference alignment, and so on. And in this talk, I want to talk about the edge removal problem and show its connections to a bunch of other problems that seem, at least at first, unrelated. So I'm going to start out with a little bit of preliminaries just to set a common ground, and then I'll go through or present the problem. So I'm going to talk mostly about noiseless networks, that is network coding. And in this setting, we're given a graph. It's a directed network. It has a bunch of source vertices, a bunch of terminal vertices. There are a bunch of requirements. This SI wants to communicate with this other TJ, and so on. And what we want to do is, of course, design some kind of flow of information over this network that satisfies the requirements. So that's the setting. And I'm going to show many different problems throughout the talk. So I'm going to give a little bit of simplifying assumptions. Some are needed, some are not needed, but I won't specify exactly throughout the talk. I'm going to have our network be acyclic. And I'm going to have edges of the network have a capacity. Each edge is going to have a capacity. Edge E will have capacity C of E. I'm going to have the sources, at least for most of the talk, I'm going to have the sources holding independent information. And I'm also going to consider the case in which the demand structure between sources and terminals is a simple one of multiple unicast, in which there are just K source terminal pairs, SI, TI, and SI wants to communicate with TI. That's the setting for most of the talk. And when I say SI wants to communicate with TI, I'll just define this rigorously or semi-rigorously. Communication at a certain rate, R1 to RK, each source SI is communicating at rate Ri, is achievable on a certain instance with block length n if the following happens. This is very natural, it's very standard. If we can assign random variables, Si to the sources and Xe to each and every edge of the network, such that the following things will happen. So what's going to happen? First of all, we want the sources to have high rate, that is rate Ri. So source Si is going to be independent and uniform with support 2 to the power of Rin. So that's the rate. We want these random variables Xe corresponding to edges. We want them we want to be able to communicate them over an edge. So we want the support of the edge to be able to capture the random variable. So these random variables are going to have support, which is 2 to the power of Ce times n for an edge E. So think of sources being generated uniformly, and random variables on edges are just random variables that can be expressed by the capacity of the edge. And of course, we want this assignment of random variables over the network to allow some kind of flow of information. So what we want essentially is that for every outgoing edge of a node, its random variable is a function of the incoming information. Again, very standard. At the end, we have our terminals. They have to do decoding. So each one has an estimate. Each terminal TI is going to have an estimate of its source that it wants. And we're going to say that communication is successful with probability 1 over epsilon if all the terminals can decode successfully. And the only source of randomness, because the network is without any noise, is just the randomness of the sources. So if we're able to communicate at this rate, I'm just going to use the following terminology. And I think this is the most kind of technical slide. I'm going to say that we have rate R1 to RK, or rate R1 to RK is epsilon n feasible if, for block length n and error epsilon, I'm able to communicate at this rate. So that's, I'm going to use that quite a lot. And I'm also going to use this kind of terminology. R1 to Rk without the epsilon n is feasible if it's feasible for every epsilon. So for every epsilon larger than 0, when epsilon tends to 0, there exists a large enough n such that I'm able to communicate. And the capacity region of a network is going to be the closure of all these feasible tuples R. So again, this is very, very standard. Okay, so I want to sort of talk about the edge removal problem that was discussed in the last lecture of Michel. Also, and this is a problem that was sort of suggested a few years ago by Michel and co-authors. So I'm given a network, let's say multiple unicast, and I know that I can communicate over this network with a certain rate tuple R1 to Rk. So R1 to Rk is achievable on the network. This network has a certain edge, E, and this edge E has a certain capacity, delta. And the question that we're asking here is, what happens to my communication capabilities when I remove this edge E from the network? So what can be said regarding the achievable rate on the new network without the edge? In other words, what is a guarantee in loss and rate when I sort of remove, or when I have one link that's failing inside this network? So what is the loss and rate when we're removing a delta capacity edge? And it's pretty easy to see that there are examples in which if you remove a delta capacity edge, the rate is going to decrease by delta in each and every coordinate, exactly like was shown in the previous lecture. And here's an example. It's just a butterfly example. In this example, you can communicate at rate 1, 1, in the sense that if each edge has capacity 1, then you can just send these bits over the network with block length 1 and communicate at this rate, and this rate is optimal. But now if you sort of maybe change this bottleneck edge into a bunch of edges, each one of capacity delta, let's say 1 over delta of them, and remove one of them, then again, it's very easy to see that the best you can do in this case is to communicate at rate 1 minus delta, 1 minus delta. So you're losing a delta capacity in each coordinate when you're removing a delta capacity edge, because for each and every source terminal pair, here we have S1 going to T1 and S2 going to T2, they need this bottleneck edge. So you lose a delta additive term in each coordinate in this butterfly example, and the question is, what is the price of edge removal in general? And here's the edge removal sort of statement. It's not known to be true, it's not known to be false, so we haven't proven it. And we don't have a counterexample for it, but it states that any network coding instance that's R1 to Rk feasible on a network N with a certain edge E. If I remove this edge E that has capacity delta, I get R1 minus delta up to Rk minus delta. So I said it's not known to be true or false, but it is known to be true in several special cases. So there are cases in which the removal of a delta capacity edge is going to give you exactly, or at most, it's going to give you this kind of loss in each and every coordinate. So what are the cases? The first case is the case of multicast communication, in which we have one source that holds all the information. All the information of this source is going to be communicated to all the terminals. So all the terminals want all the information. In this case, if you remove any edge of capacity delta, then you get a delta decrease in rate at most. Sort of similar is the case of co-located sources. In co-located sources, again, we have one source node with all the information, but now each and every terminal may want a different subset of information. So again, in this case, what you get is that removing a delta capacity edge, you're losing just delta at most. And if your network has coding functions which are linear coding functions, then in that case you can also prove that removing a delta capacity edge, it just allows you a loss of delta. And the question again, is this true for any network coding instance? And you can relax this problem a little bit and not think of this very strict requirement going from this rate tuple R1 to Rk to a rate tuple of R1 minus delta to Rk minus delta, you can think of a more asymptotic edge removal statement, which it's a little bit dense, but which says essentially the following. Let's say that I have a network and my edge, my delta capacity edge is really delta capacity in the sense that delta is a small, very small, let's say negligible capacity. So I can have block length n and I can have the edge being of capacity log n over n in the sense that it communicates only log n bits. So if my edge has very, very low capacity, vanishing capacity, is it the case that it affects my rate tuple also in a vanishing way when I remove it? So even this asymptotic edge removal statement, which seems very, very natural, if I remove a negligible capacity edge from the network, I shouldn't get that much of a change, or maybe, yes or maybe not, in the new network when this edge is removed.
So Mike, to understand, so for the linear code case, for example, you say, to prove this, you say I have a linear code, it's making everybody happy, now I lose that edge, I have to make a new linear code that doesn't use that edge, that still makes everyone happy and has rates, that all the rates drop by delta, right?
So I'm saying something a little bit different. I'm saying that if I have a linear code on my network and I remove a delta capacity edge, I have another code. By chance, it's also linear. But the thing is that I have another code on the network without the edge that's not far away from it, only delta far away.
The linear code that you construct in this proof, is it over the same field?
Yes.
And is this true for vector linear also?
I'm not completely sure. I have to think about that. I'm not sure. Because essentially the proof here uses it uses the sort of it zeroes out a matrix and it uses the zero space of a matrix, which is a linear transformation, and it could be maybe extended to also vector linear, but I'm not completely sure. Okay, so the edge removal statement is not known. The asymptotic edge removal statement is not known to be true, and the question is what can we do with it? So it seems like a very simple problem, but it's currently open. So before we sort of maybe talk about what we do with the edge removal problem, if we would know that it's solved, let's see what happens in noisy networks, because what we're thinking about is network coding, which was up to now noiseless networks. So if the networks are noisy, edge removal does not hold. So this is known not to hold. I'll show two examples, one for adversarial noise, one for memoryless noise. So think of communicating over a network in which has like a jamming adversary. So if you think about point-to-point communication, you can think of a sender X or receiver Y. This is a binary channel. You're sending n bits, and the adversary can flip, let's say, pn bits out of this channel. So that's, of course, just point-to-point is a very well-known model. Let's add a very low rate, negligible rate side channel between X and Y. And now in this network, which has both this channel which can be jammed and the side channel, the way you can communicate is by sending some information over the channel. Y can now list decode instead of unique decoding, and you can sort of send either a hash, or you can just send any actually random string over this channel. It's going to help Y disambiguate. So over this channel, the communication rate will be the list decoding rate. But of course, if you remove this link, then you're back to the standard unique decoding rate, and so there's a big gap. So in this case, in adversarial noise, if I remove this edge, which is negligible, it's like log n bits out of a block length of n, then the rate drops dramatically. And we have a similar example in the memoryless noise case. So in this case, we're looking at the multiple access channel. And in this multiple access channel, you have two senders. They're independent. They go through a channel. Y wants to decode. And in this case, also, we add some kind of gadget. Here, the gadget was very simple. Here, you can add a gadget. We call this gadget a cooperation facilitator, in which it takes all the information of X1, all the information of X2. It does some kind of computation. And then, in a very low rate channel, it gives back information to X1 and to X2. And once you have this negligible channel between that gives additional information to x1 and x2, you can get a high rate of communication. And if you remove this channel, the communication rate drops dramatically. Specifically, we design a certain channel that has this property. Not for all channels this will happen. But for adversarial noise and for memoryless noise, removing an edge can have a significant effect. Yes.
So this is clear in the delta case. Is this also true in the continuity case?
So these two examples are actually in the continuity case, in the sense that this edge is log n over n capacity, and this edge is going to have capacity which is any epsilon that I want. It's not vanishing, but it's going to be any constant epsilon that I want. So the trick here is that we need the alpha bit size to grow with the capacity of the edge. So there's a little delicacy here, but this is truly asymptotical. This is almost asymptotical. Okay, so what's the price of its removal? It's not known, not even this relaxed statement. And the challenge in general in improving this edge removal problem is that we have a code for n. We want to design a code for n without the edge e, and designing a code for n without the edge e turns out to be pretty challenging. But, and this is the whole idea of this paradigm of reductions, we don't know the answer, but we can still understand what the implications would be if the answer were true or if the answer was false. And what I want to show now is just a bunch of different other problems that are related to the edge removal problem that at first seemed, at least to us, unrelated. So I'm going to talk about implications on reliability in network communication, on topology of networks, on the demand structure, and on cooperation in general in networks. So I'm going to show these connections. Okay, let's start with reliability, and I'll present another question, which is the 0 versus epsilon error communication question. So again, our starting point is a graph, multiple sources, multiple terminals, and we have this multiple unicast communication requirement. And let's say that we can communicate at rate R1 up to Rk on this network, but we can communicate only when we have a probability of epsilon. It could maybe tend to 0, but we have always some probability of epsilon that our communication is going to fail. And in this question that we're raising, we're asking, okay, what happens when I want to insist on 0 error in communication? So I know that R1 to Rk can be achievable when I have a little bit of error. What can I say when I want to insist on 0 error? So again, what is the cost in rate that I have to pay when I want to make sure that I'm communicating at 0 error and not at epsilon error? So in general, if one asks, okay, can I obtain a higher rate of communication when I'm allowing epsilon error not as opposed to 0 error, the answer in general networks, noisy networks, in particular, the answer is going to be yes, epsilon error helps. If there's some error, you can get a higher rate. One example, even in the case in which there's no noise, but the sources are dependent, is the Stepien-Wolf problem. The sources are dependent. If I want to succeed for most cases, I can do it with very high rate. If I want to succeed for all cases, that is with no probability of error, then the rate significantly reduces.
Average over the set of messages or the sources, or is it maximum over the messages?
So what we're doing here is our networks are noiseless. So the only source of randomness is the sources, the source message. So because if you have, exactly. So if the network has noise and it's not a noiseless network, then of course you're going to benefit from epsilon error as opposed to 0. So we're asking, okay, we're assuming independent sources and noiseless network, and we're asking what happens in this case. What about the network coding scenario when there's no noise and all the sources are independent? Again, is there an advantage in epsilon versus 0? Okay, so up to now we had 2 problems, the edge removal problem. Yes? 5 minutes left? Yes. Really? Okay, so I'm not going to finish the talk, but I'll do it a little bit faster. For me, it was a surprise. So how many would believe that the edge removal statement is true?
Oh,
I'm asking, yeah, I'm just asking.
Yes.
I don't have time anyway, so I'm going to ask questions. And what about the epsilon versus zero error?
What is the...
I don't know about
Okay, so the statement would be something like this, would be that if I'm R1 to RK feasible with error epsilon, then I'm going to lose a little bit if I insist on zero error, but this little bit, delta, is going to depend on you.
I don't believe actually vote in either statement. So I vote no for both.
So my intuition, at least, was edge removal true, zero error false. But it turns out, and I'll just jump ahead because I'm a little bit short in time, that they're the same. So it turns out, for example, that edge removal is true if and only if the zero error.
But neither is known.
But neither is known, yeah.
At least I'm consistent.
So the edge removal statement is true if and only if this zero error statement, which I went through very quickly.
the zero error statement.
So you want me to repeat it? So again, it says something of the sort that if I'm R1 to RK feasible with error epsilon, and epsilon is, can tend to 0, then I'm losing a little bit in rate. I'm going to be R1 minus delta RK minus delta feasible with 0 error in the network coding regime. And the way we prove these kind of results is again, we don't know if the edge removal is true or not. Yeah, so both directions. So the flow of the talk, originally I wanted to say that this has two directions, of course. And for example, proving one direction, it will have the following kind of flavor to it. We're assuming that we can communicate with epsilon error. We're also assuming that edge removal is true. And we'll show that you can communicate at 0 error with a little bit less. So that will be one direction, the other direction is similar. So this is an if and only if statement. Okay, so I have to replan. So how much more time do I have? I'm going to jump very quickly.
The program says noon is lunch, so you can cut into lunch, but you may get in trouble.
No, but for noon, how much time?
For noon is like 3 minutes.
Ah, okay, good. Okay, so what I'll do...
Yeah, so maybe you started 1 or 2 minutes late, so
I'll do one more problem, then I'll jump to the end. Okay. It's very nice. Yeah, you're a very nice chair. Okay, I'll do it quick. 3 minutes, okay. So I want to talk about topology of networks also. So as Michelle mentioned, recent studies have shown that there's connections between network coding and index coding instances, in the sense that we can take any network coding instance, turn it into an index coding instance, in such a way that if we solve the index coding instance, we can get a solution to the network coding instance. So this is recent work, and it's a very nice reduction, or I think it's a nice reduction in the sense that somehow it allows to separate the difficulty, or two difficulties in network communication. One is that the fact that we're looking at a topology, and the other one is that we have to encode. So if you have to encode information also when you're insisting of preserving these topological constraints, it becomes more difficult. And here, if we're reducing everything to index coding, it's simpler because there's only one node that does encoding. Okay. So there was an issue in this reduction, is that it says that any network coding instance is R feasible if and only if its corresponding index coding instance is some R prime feasible for some function of R. In general, what it does, it takes any code in the index coding regime and it's going to turn it into a code in the network coding regime. And pretty surprisingly, this does not extend to a reduction which answers the following very related question, which is, can one determine the capacity region of, a network code using the capacity region of an index code? So it's kind of subtle. I can design any code for network coding by studying a similar code for index coding. But doesn't that mean that I can actually characterize the capacity region of a network coding using the capacity region of an index coding? And the answer is no. The problem is that this reduction breaks down when you look at the closure operation. So there's still an issue of closure. And again, one could ask how to overcome this, and this was open, and it's been a difficult and challenging problem, but I'll just say in one word that edge removal resolves this also, and just like the previous case, we get an if and only if connection in the sense that we can characterize the capacity of network coding with the capacity of index coding if and only if this asymptotic edge removal statement is true. I'll actually jump almost to the end. And you didn't see this, but this edge removal statement turns out to be not only connected to the 0 versus epsilon error condition, not only to the fact that we can connect between reduction in capacity and reduction in code design for index coding, it also is connected to the difference between communicating over a network with dependent sources and communicating over a network with independent sources. And it's also connected to the fact that you can communicate or take any network with many different communication demands, SIs, TJs that want SI, and turn them into a very simplistic network. There's a beautiful recent work that is just a 2 unicast network. So edge removal sort of connects all these problems together, or open issues in all these problems. And again, just maybe one other way to view this is that this edge removal captures the notion of slackness, and it shows that different types of slackness are equivalent. So what do I mean? If you think of removing a delta capacity edge and wanting the rate to reduce by delta, it means that if you have a slight slackness in edge capacity, it doesn't really matter. The 0 versus epsilon error statement says that if you have a slight slackness in reliability, again, it doesn't really matter. This notion of capacity reduction versus code reduction says that if you have a slight slackness in this notion of closure, it also really doesn't matter. So it could be, and this is sort of work in progress, and we want to define this rigorously, but it could be that all these forms of slackness are actually equivalent, and these problems or this statement came to life by studying this edge removal problem. So just a few minutes later. Okay, thank you.
So, any questions? So I have one that I have been thinking a bit. So for example, none of these reductions explicitly discusses the issue of approximation, right? So let's say I had a multiple unicast algorithm that was within, let's say, a log k factor from, which by the way I believe is possible to do for sum rate. So for the sum rate for multiple unicasts approximating within, let's say, a log k factor, where k is the number of sessions. How would now, in this reduction, for example, you mentioned it can be reduced to 2 unicasts, how would my approximation factor change? So
it's a good...
This was never discussed, and I think it's a very important point.
So we do have a work which proves that you could not approximate the multiple unicast communication problem within a certain factor alpha. If you do, then this sort of gives you some type of coloring of a graph.
For sum rate?
For...
That's why I thought
I think sum rate will follow from this, because I'm pretty sure that sum rate will follow from this, but this I have to check rigorously. But this does not rule out the log, maybe log n and not log k, but a log n approximation. It doesn't rule out a log n approximation. And your question was, how do these preserve approximation or not? And actually, I didn't think about that, so that would be nice to discuss that, but I'm not completely sure.
So you have to open all these proofs and see very carefully where you get that. Any other questions?
So do you believe the edge removal?
So it was funny because we were trying to prove the edge removal conjecture, and in parallel I was trying to find a counterexample for the epsilon versus. And we're sort of pushing on both of these pretty hard. So actually, I'm not completely sure.
Right. Let's thank Mike and everyone.